And up to now, anytime we wanted to take a derivative that involved time, the variable t would appear in the equation we were going to take the derivative of. And so up to now, up to this section, if you wanted to know, oh, how fast is the population changing, or what's the velocity, or what's the acceleration, the time always appeared, usually as a t, in the equation. What's going to happen in this section is we're going to be knowing how fast something changes with respect to time, but time's not going to be part of the equation. So give you a couple of examples of the types of things we're going to see, the problems we're actually going to see. Suppose we have a spherical snowball. Okay, perfect sphere. We're going to be in the world of everything's a perfect shape, so don't laugh too much at it. But perfect sphere, perfect spherical snowball. And that snowball is going to melt. And we're going to be talking about either finding how fast the volume of the snowball changes, or the surface area, or some geometric formula, versus how fast the radius changes. And what's going to happen is the formula is going to have volume and radius, but we're going to have this time factor in. And what's happening is the radius is changing with respect to time, the volume is changing with respect to time, but the formula itself doesn't have the t in it. Those problems are the ones that become related rates. You get the related piece because you have one variable related to another variable, and the third thing connects them. That third thing is time. So that's kind of the game plan that we have. Just before I forget, since I know at Copenhagen you said that you have a sub-room monitor, if that person's taking attendance, Ryan's here. So I don't want Ryan to get marked absent, although probably if he did get marked absent, everybody would say, well, yeah, Ryan, we know where Ryan is at that time of the day. But so that's kind of the concept. So let me show you, I'm going to put a problem or two up here that is not a related rates question, and then we'll go into the related rates. So exactly what you're going to see me use here are exactly the notes that you'll be getting. So I'm going to actually follow through on the notes. They are coming up good. Because this thing is not. Let's see if it'll. There it goes. I was going to say it wasn't coming up on my screen, so I was a little freaked out. It's a little hard to look backwards and forwards at the same time. So, the first thing, though, it really was this rates of change piece. And this is what we've already talked about. You know, here's the example of the rates of change. Find the rate a population is changing at t equals 10 years if the population is given by p of t is 2,000 times 0.95 to the t. So again, notice time is a variable in this particular function. And so this problem is done really as a regular derivative. And the concept is this is a regular derivative. And so we just take the basic boring derivative, 2,000 times 0.95 to the t times the natural log of 0.95. Remember to take that derivative. The 2,000 is a constant. It's along for the ride, so I just took the derivative of the 0.95 to the t, which is this part. And then we plug in the 10 and put on our units. We've done that numerous times before. It's not a big deal to us. Well, here's the snowball question, and I'm going to actually cover up a chunk of this so that you can kind of watch us go through it here. So this is the situation. This is kind of what's going on. We'll talk a little bit about the process here. So here's the snowball. Spherical snowball's melting. Its radius decreases at a constant rate of 0.75 centimeters per minute from an initial value of 60 centimeters. How fast is the volume decreasing when the radius is 10 centimeters? Now, actually in this one we have a little bit of extra information. Sometimes they give us some extra information, but notice as we look at this, we're looking at this and as I'm trying to figure out, okay, what is it I want to do? Well, when I look at the question, I'm looking for that rate of change word. So I'm looking for the how fast and decreasing. And so that's the part of the problem I am looking for. And connected to that is this thing called the volume. And I know I have a spherical snowball. And so that information right there tells me that what I'm working with is the volume formula. And so I need to know something about the volume of a sphere. And this is where I tend to try to be a little bit nice, although most of you probably after you do 2 or 3 of these, you don't even need me to be nice. When we're looking at the volume of a sphere, we need to know the formula for it. And probably right about now, unless you were looking real quickly at what I had, you probably wouldn't necessarily remember the volume of a sphere. But there's our volume of a sphere formula. V equals 4/3 pi r cubed. By the way, when I take the derivative, I'm going to kind of show you something that I think is kind of cool. So we're going to be using it. Look at that formula. It doesn't have time in it. But look at the information they gave me. They gave me information someplace in the problem that includes a rate that involves time. Those two together, a formula without time and some information given in the problem that does involve time, tell me related rates. And so that, for many students, that's the hardest part of the problem, is recognizing that they need to do related rates. So, there's kind of that step. But I'm going to be writing down the steps, and then I'm going to uncover exactly the same step. So what it is, we get the formula. Not a big deal. Then typically, once we have the formula, and we typically, not always the case, typically we, again, kind of like what we just did, we really would like it to only have one variable. So there's going to be occasions where we're going to have two. We're going to be doing some cone questions, and cone questions involve both the radius and the height. And so we're going to actually do something to get rid of one of the variables, kind of like we did before. Once we do that, what we do is we take the derivative with respect to time. Now you might say, what does that mean? Well, if I just take the derivative the way this is, if I think of my old derivatives, this really would be the derivative with respect to the radius. Because I do dy over dx, and so it'd be dv dr typically. What I'm really thinking of is the following. This is the way I think, although you won't see me write it down, is that what I actually have is somehow a velocity that somehow is respect, or a volume that somehow is respect to time, and a radius that's somehow with respect to time. So what's occurring here, I won't ever write that down, is when I do the derivative on a related rates problem, instead of writing v prime, I'm going to write dv dt. It's going to be the change in the velocity with respect to time, or not velocity, volume with respect to time. Boy, I want to say velocity today. So it's the change in the volume with respect to time. And then I just take the derivative here, same deal with respect to time. 4/3 and pi are constants. This will happen a lot in these problems. They're along for the ride. And then I just take the derivative of r cubed. And the derivative of r cubed in these problems would be 3r squared. And then it's a little bit like the implicit derivatives we did, and it really is much more closely related to those. What we do is we take the derivative and then we'll be multiplying by dr dt. So it's much more implicit, like where we put the y prime at the end of things or the dy dx at the end of things. It's going to be the same kind of process. All of our derivatives are with respect to time. So instead of writing v prime, we write dv dt. Instead of writing r prime, or instead of just taking that, we have to tack on this dr dt. And if I slide up my thing, you'll notice that I did that and I actually simplified it. Notice this 3 and that 3 cancel, and so it gives me 4 pi r squared dr dt. Ta-da. Now, I'm going to stop here a second, and I just want to make a little comment. And when I realized this, and I actually learned this or realized it in Calc 1 myself, this right here is the formula for the volume of a sphere. When I take the derivative of the volume of a sphere, ignore the dr dt for the moment, that actually gives me the surface area of the sphere. The derivative of the volume formula gives me the surface area. And so if I ever want to know the surface area of a sphere, all I do is I actually have the volume memorized and I just take its derivative and it gives me the surface area. Similarly, little side visit, this is kind of a cool thing that happens with circular things. There's the area of a circle. If I take the derivative of it, and I'm going to just not do it as a related rate, it gives me 2 pi r, which is actually the circumference. That was something I thought was really cool. If you take the derivative of the volume of a sphere, it gives you the surface area. If you take the derivative of the area of a circle, it gives you the circumference. I'm probably the only one in the whole room that's excited about that. But, you know, gets me, you know, I need to be excited once in a while. Now, on this problem, we're now down to the what I think of as the easy part of the problem. Let me widen this out a little bit. Now what we do is we put in everything that we know. And notice it's saying, how fast is the volume decreasing? So that's what we're actually looking for. So what we need to be able to do is put numbers in for the things on the other side. So 4 pi are, those are already numbers. And notice that they want us to do this at exactly the instant when the radius is 10. So I put that in for my r. And then in for my dr dt, I put in the number they gave me. Now I have to be a little bit careful. Because what I've actually written down isn't 100% correct. There's a little teeny tiny thing I have to put someplace in here. Anybody want to make a guess as to what that teeny tiny thing is? Not a bad idea, because I gave you that number. It seems like you should do something with it, but we don't actually.
Negative in the 0.75.
Oh, did you just hear what Ryan had to say? Ryan, could you say that again?
A negative because it decreases on the 0.75.
The 0.75 is decreasing, and anytime we're doing these problems and something's decreasing, that rate will be negative. And so since this is actually a decreasing number, what this number actually tells me is that dr dt is negative 0.75. And now I just pop this into my calculator, and I can cheat. If I pop that into my calculator, it's going to give me negative, if my math was correct, 942.5. And notice I put the units on here just so you would see that they work. This is going to give me a centimeter squared and a centimeter, so that gives me centimeters cubed per minute, which makes sense because I want dV dt, and volume units should be centimeters cubed, and time units are minute. So I always check my units just to make sure, because if my units are correct, then more than likely I'm in pretty good shape. So now that's kind of the basic concept of what we're doing. So what you'll see in the notes is actually the set of steps that we pretty much did. if we're going to do a related rates problem, first of all, you probably have to identify it's a related rates problem. The first thing that I tend to do is almost exactly what you just saw me do. I kind of analyze the wording in the problem. What am I looking for? What they give me? So I identify kind of what's changing. Sometimes you want to draw a picture. Probably drawing a picture of a melting snowball would not have helped us a whole lot here. Then we write down an equation that relates those changing quantities. We differentiate both sides of the equation with respect to t. And there might be some rephrasing. Your textbook uses that step. And then really the last step is substitute what's given to obtain the required quantity. Fairly straightforward process, and some of you might be saying, okay, lady, you said this is hard, but that doesn't seem so hard. It's a couple of the problems that are weirder, and it has a little bit more to do, again, with knowing that it's a related rates problem. So let's just rattle through a few. Again, because I'm recording this, I'm actually going to rattle through them and probably not write down much. What'll be really cool is once you have the notes, or if you want to go back and look, that you'll be able to kind of get my actual words over and over and over again. Again, it's my attempt to try to make it so these aren't quite so ugly for you. One of these always appears on the final exam. Usually it's one of the harder versions. Usually it's not the sphere, usually not the doggy puddle. It's one of my favorite. The area of a circular doggy puddle. Like, how many doggies do you know that leave a puddle that's a perfect circle? But, oh well. Area of a circular doggy puddle is growing at a rate of 12 centimeters squared per second. How fast is the radius growing at the instant when it equals 10 centimeters? And so, again, I could draw a picture, probably not going to be terribly helpful here, but we could. What I tend to do is I tend to look at the numbers that they gave me in the problem, and I look to see what it is they're looking for me to give. So, looking at the first sentence, the area is growing at a rate of 12 square centimeters per second. The wording and the units tell me that this has to be dAdt. It's the change in the area with respect to time. And notice it's growing. And so therefore that 12 is positive. And then notice what they're asking us is how fast is the radius growing. So they really are looking for us to tell what is dr dt when it, meaning the radius, is 10 centimeters. And so I've kind of analyzed what they're looking for and what the numbers are as I move forward. So, see that step one I said? Identify the changing quantities, possibly with the aid of a sketch. Well, radius and the area. And I actually did some of the number stuff of what they are. Step two said write down the equation. Well, it's the area of a circle, right? Circular doggy puddle. So there's my formula. Area is pi r squared. And so again, remember as I said before, we could think of it as technically as being functions of t, so we could think of it that way, although you won't typically see me write it down that way. Then we differentiate both sides of the equation with respect to t. So, and then normally, and as I said, normally it's this equation. So there's my dA dt is 2 pi r dr dt. If we actually were doing the other one, just so that you see it, we'd actually have a prime at t and then 2 pi. And when we want to take the derivative, we would use the chain rule here. So we'd have 2 r of t to the first times the derivative of the inside, r prime at t. So there's that dr dt that we're seeing. So it does actually fit and work for us. And so there we are back at that formula. Now we just put in what we know. Now if I go back to the question, I already identified that dA dt is 12, and I know that r is 10, and I'm looking for dr dt. So notice if I come down here, that's what I'm looking for, and I have the dA dt, and I have the r. And so I did the wording, I wrote kind of the wording, but you'll notice if I do that, what I would get, and I kind of skipped a couple of the steps, so let's just kind of write that down. I knew dA dt was 12, is 2 pi, r was 10, dr dt. And there's the 12 divided by 20 pi, or approximately 0.19 centimeters per second. And notice if I put the units on, I would have actually had units that were centimeters squared per second equals, and then here this 2 is a number, this 10 is a number, this would have been centimeters, and then dr dt, and when I did the division, there gets me my centimeters per second as my units of dr dt, which I expect they should be. It should be radius units divided by time units. I will warn you, occasionally the book tries to be tricky, and in trying to be tricky, what the book will sometimes do is they'll give you some of the units in seconds and some in minutes, and you need to convert at least one of the numbers, and usually you want to convert it into what they're looking for the answer. So just be aware, it's sometimes, or they'll do that with inches and feet, that you need to be always in inches or always in feet, and that can mess you up a little bit. So that's the most straightforward version. Now we're going to get into some of the little squirrelier ones that occur. This next one's not terribly squirrely, except the formula is a little squirrely. Not horribly, but enough that it freaks people out a little bit. So what we have here is, this is like the classic. By the way, I'm doing all the classic related rates questions. The sphere, I'll tell you that the ones that you almost always see, you almost always will see in books, in exams, and things of that nature. You see the spheres, the circles, this one's going to be a triangle question, and cones. And then almost everything else that you do is some variety of that. There is one trigonometric situation you'll sometimes see, but it's really like circles, spheres, cones, triangles, pretty much the classic stuff. So I'm going through all the classics. You open up any Calc 1 book, and they'll all have these problems. Different words, different situations. So here we go. I have Jim. He's perched. By the way, my husband's name is Jim, so every once in a while he sometimes ends up in my problems. He probably would not be terribly happy that I created this particular problem, but oh well, he's not here to defend himself. Jim is perched precariously on the top of a 10-foot ladder, leaning against the back wall of an apartment building, spying on an enemy of his, when the ladder starts to slide down the wall at a rate of 4 feet per minute. Jim's accomplice, Lou, is standing on the ground 6 feet away from the wall. How fast is the base of the ladder moving when it hits Lou? This is one where a picture is helpful to us. And we are going to, on any of these problems, we're going to make an assumption unless we're told otherwise. And that assumption is that the triangle that's created is a right triangle. Yes, it's going to be important that it's a right triangle unless you're told otherwise. So, I'm going to draw a picture of the situation. So, There's my husband, top of the ladder, peering over the wall. The ladder is 10 feet long. And so this right here is the ladder. And what's happening is the ladder is going to slide down the wall, and as it does that, it's going to move out. So notice as we look at this, notice how I've labeled this. I've labeled an X and a Y, because I have this right triangle, and so I know some things about right triangles. Notice as I look at this, with this problem, I'm actually going to be dealing with a dy dt and a dx dt. As I'm doing this problem, what is going to be the sign, the SIGN sign, of dy dt? Yeah, it's going to be negative. Because y is getting smaller, but dx dt is going to be positive because the x is getting bigger. So I'm going to just label my good old right triangle. That's pretty typical for what we do. Now, notice what they gave us. Notice I can put this 10 in here. Sometimes I can't put a number in, but the ladder is going to stay the same length. And anytime something stays the same length through the entire problem, you can pop the number in right away. If that number changes at all during the problem, you cannot put that number in to start. It becomes one of the numbers you put in at the very end. So, notice the ladder is going to slide down the wall at 4 feet per minute. What is that? What is that 4 going to be connected to? It is, yeah. And so what this tells me is dy dt is actually negative 4 feet per minute. We already said it's negative. And then Jim's accomplice Lou is standing on the ground 6 feet away from the wall. That is eventually going to be, it's not what I use right off, but that's eventually going to be the X that we're going to be using. Now, I'm not going to be able to just put 6 in the problem right now because it's not 6 for the whole problem. It's only 6 at a particular instant in time. So I can put the 10 in because that's always 10. But the 6 is not 6 for the whole problem. It's actually the instant that we're worried about. And so they're asking how fast is the base of the ladder moving when it hits Lou. And so this right here is actually what we're going to be looking for. So what I'm going to have to do now is find that step 2 of an equation that's going to relate all of this together, that I'm going to be taking the derivative of. And this is one of those, and I told you that typically we'll have one variable. This actually is, I'm going to call it the one situation, but it really is the one situation that we're going to do where we'll actually keep both the x and the y in the problem. Could do area of a triangle, but did we get anything that has to do with area? No. Did we see the word area in here? No, probably not. What kind of a triangle is this? A right triangle. When you hear right triangle, in your world, is there anything from, maybe as far back as 5th or 6th grade even, that comes into mind when you have a right triangle? Yeah, I'm hearing several people mutter it. The Pythagorean theorem. These triangle questions, if you're not told area, if they don't use the word area or perimeter or something, they're typically Pythagorean theorem questions. So what I would do is I then would, okay, came back, but it didn't come back on my screen. There it goes. It's a little groggy today. So we use the Pythagorean theorem. And using what I have there, that would be x squared plus y squared is 10 squared. And this is the one case where I'm going to keep the two variables on the same side. I could, by the way, to make it look a little bit more like the others, I could solve for one of those variables so it does look like v equals blah, blah, blah. Notice no matter what in this problem at this point, I still do have just two variables, just like the others. But there are occasions where we might actually have x squared plus y squared is z squared, and we have enough information that we're going to use all three. The Pythagorean theorem's really the one where you start to see multiple variables roaming around. Then what we do is we take the derivative. Notice again, I put the 10 in because that's 10 for the whole problem. Otherwise, I wait till the bitter end to put in any number. So I take the derivative of x squared is 2x, and because it's a related rate, because there's no time in the problem, but I clearly have time going on, 2x and I do dx dt, derivative of y squared is 2y, I do dy dt, and the derivative of 10 squared is 0, because it's a constant. Then, just like the other problems, I put in what we know. And this is one of those where there's one piece I don't know that I will be able to deal with in a minute. So what I know from what they told me is this is 10. I know dy dt is negative 4 feet per minute. I know when it hits Lou, when Lou's here crashed on the ground, I know this is 6, and that's my x. So what I can do is I know I put the 6 in here. I know I put negative 4 in here. This is actually what I'm looking for. Notice the one piece of information, and I'll zoom this back in so that you don't have to squint any more than you have to. The one piece of information that still is outstanding is the y. Now, it's not something I'm solving for, and it's not something I'm given. But it's a right triangle, isn't it? And so at the instant I'm worried about, and this is sort of rigged, this side is 6, the hypotenuse is 10. If you know your Pythagorean triples, you know that this side at that instant in time has to be 8. Yep. And so then I can stuff the 8 in. Once in a while, you have to use the formula to find one more number to be able to plug into the end. That's what all of this is saying. So I substitute in 2 times 6 times the x dt plus 2 times 8 times negative 4 is 0. If I do the math, I end up getting 64 over 12 or 16 over 3, and it is positive. Feet per minute, I could write that as a decimal. I left it as the value that's there. Again, when you look at this, most of you are probably going, okay, yeah, I got that. And again, I don't know exactly what I say that's confusing or exactly what my Calc 1 instructor told me that was confusing. I remember these just being like poke and hope. But they almost all, and we tend to be pretty predictable on the final exam, and on anything, they tend to fall into one of these cases. And so sometimes I'm like, I get a little frustrated. I'm like, oh, we did 4 of those. And oh, we had them. But hey, it is what it is. I want to do the hardest version of them now. How am I doing for time? And so I realized, maybe I'd look at the clock. This is the hardest version. And it's not that hard, but I think it's because it has some steps in it. And these falls, sometimes we're going to build cones, sometimes we're going to get rid of cones. So here's the example. Sand is being emptied from a hopper at a rate of 10 cubic feet per second. Let's just stop right there. Let's look at the units. Volume. That's, yeah, we see the cubic feet. This is volume. This right here is going to be our dVdt. And notice what it's doing. It's forming a conical pile. So it's coming out, so it's forming a conical pile. So is the volume getting bigger or smaller? Bigger. So this number is positive. And it's forming a conical pile whose height is always twice its radius. So this actually tells me H is 2r. At what rate is the radius of the pile increasing when its height is 5 feet? So when I look at this, this is telling me I want rate of the radius. So this is telling me that's my goal, is to get dr dt. I'm going to tell you, all these cone problems are done pretty much the same. There's kind of two versions we'll see, and this is the easier version. So, we have volume, we have radius, we have height. We need the formula. So there's our conical pile, by the way. I drew a little pretty picture. There's the volume of a cone, of which most of you probably don't remember. No. Ryan shook his head no. But 1/3 pi r squared h. These cone questions are always done in a way that we get rid of one of the variables before we take the derivative. We will always get rid of one of the variables. The variable we want to get rid of is the one that we don't either have information on or is the one that we don't want to find something out about. So notice here, we actually want to find the rate of the radius. So this actually is kind of telling me, keep r, eliminate h. Since they're asking me something about the rate of the radius, that's indicating to me I probably want to keep r, get rid of h. Which helps out nicely because I know h is 2r. And so I can actually, and you'll see this on the paper, I can just put that in. And if I do that, that then gives me the volume's 2/3 pi r cubed. Now guess what? This looks a whole heck of a lot like the snowball question, doesn't it? Looks almost identical, a little different formula to the snowball question. Take the derivative, dv dt. Notice if you're going, wait a minute, how'd you get this? Notice when I take the derivative here, it's 2/3 pi 3r squared dr dt. And the 3's cancel, giving me that 2 pi r squared dr dt. Again, the item that I just boxed is what I'm looking for. Go back to the question. dv dt is 10. Only other thing I need to know is the radius. Well, I didn't tell you the radius is what the radius is. I told you the height is 5 feet. So, but I know that the height is always twice the radius. So therefore, when the height is 5, the radius has to be 2.5. Do the math. Get the answer. And again, if I check my units, it's radius units over time units, so feet per second. And notice the answer is positive since the base of the pile would need to be getting wider. The R is getting larger. I have one more cone question, and then we'll see where we are. I might just take the second to look at a couple of others next time. But this is the other cone situation. And this one sometimes also becomes a triangle situation. I'll give you the triangle situation. I'll tell you about it when we get done. Here we go. Water tank in the shape of a cone with a vertical axis and vertex pointing downward. The tank has a radius 3 feet and it's 5 feet high. That's the full tank. At first, the tank is full of water, but at time t equals 0 in seconds, a small hole in the vertex is opened and the water begins to drain. When the height of the water has dropped to 3 feet, the water is flowing out at 2 cubic feet per second. At what rate in feet per second is the water level dropping? So, what is this indicating to us? Yeah, the volume changing. So dV dt. When I put this in the problem, is it a positive 2 or a negative 2? Yeah, I think it's negative because the water is flowing out. So the volume of water is actually getting in the tank. So this is actually going to be a negative. And the water level is dropping. This actually that I'm looking for is actually going to be the dH dt. Since I'm looking for dH dt, when I do this cone problem, that's probably telling me I want to get rid of the letter R this time. So, draw myself a picture. I'm pretty proud of myself with my little paint program on some of those. So there's my picture. Notice the full cone is 3 and has a height of 5. And there's the generic R and the generic H. And that's what I'm going to need is a generic R and a generic H. Again, formula for cone. Now, remember in the last problem I told you H equal 2R? I didn't tell you that here. But by giving you the dimensions of the original cone, I've actually given you something similar to being able to tell you H is 2R. I've actually told you the ratio between H and R. Now, most of the time, some of you may be able to figure that out, but most of the time, what you want to do is you want to think of this kind of in a two-dimensional situation and realize that you have similar triangles. And when you have similar triangles, the lengths of the sides are in proportion. And there's lots of ways you can do that. You know, I typically do side to side is side to side. So I would typically say 3 is to R as 5 is to H. And do a little bit of math with that. So there's my picture. And so there's my whole conversation about similar triangles. There's my 3 is to R as 5 is to H. So 3H is 5R. And notice I said we want to keep the H in the problem. So I'm going to solve that for R. So I get R is 3/5 H. And now the problem with that becomes identical to what we just did in the previous problem. It's the ratio part that sometimes gives students some trouble. So I put the 3/5 h in for the r. Remember, it was 1/3 pi r squared h. So that goes in for the r. Convince yourself of the math. Notice this is 1/3, and that would give me 9/25, hence the 3/25 that we have. Take the derivative, dv dt is 9/25, pi h squared dh dt. And then we're going to substitute in. So they gave us dv dt. We're looking for dh dt, so we need to go back and get h. So I go back to the problem. There it is. I go back to the problem. It says, when the height of the water in the tank has dropped to 3 feet, so they actually did give me the height, didn't they? They did give me the h to use at the instant that I'm looking at. And so there we are, putting that in, putting the rest of our numbers in, and we do the math. And we end up getting that h is negative 0.196, which we expect to be negative because the height is dropping. The height's getting smaller. Again, I don't think they're that hard. They tend to give students trouble. And I think it's because of a couple of things. One, we're near the end of the semester and your brain is fried. Two, every problem is just a little different from the other one. But they do tend to all have the same kind of setup. There is one, and I'm not going to do the weather balloon problem, there is one that actually in the past has appeared on the final exam. I'll make sure I do something like it next class. I haven't seen the final. But it's this kind, and I won't draw the picture right, so don't laugh at me too much. Yeah, I always get the triangle upside down. It's this triangular trough, and they want you to do the volume of the triangular trough, and you're going to be doing dv dt of the triangular trough, and so you need the volume. And there's two things that go on. People are like, I never learned that volume. Well, the cool thing, and I don't know if you knew this or not, and it's another one of those things I learned in my Calc 1 class, is if you need the volume of any shape where the top and the bottom are exactly the same. So let's pretend I drew something that's exactly the same. It actually, the volume is always the area of the base times the height. And so the volume here is actually the area of the triangle times, and I'll call it the length. And that's the part that gives students trouble. And then what they don't realize is in this trough question, it's actually a modified cone question. Because what you're going to have is that triangle on the end. And what's happening usually is that the trough is filled with water, and you're either filling it with water or draining the water. And so you're actually setting up that kind of an R1 is to R2 as H1 is to H2 situation to be able to solve it. That one has appeared on the final. I might pull one of the old ones and bring that in and take a look at it. But that one, sometimes students will be, oh, we didn't do something just like that in class. We have, it's just the formula's different. And what you just need to realize is any time, and this is a good thing for future time, anytime you have this kind of regular shape, it's the area of the base times the height. Okay. Well, why don't we call it quits here? I have a meeting that I'm running to, and I know I have to actually get this thing to stop recording, so we'll call it quits there. And what we'll do is we'll take a look at some more of those. I said we're gonna meet on Friday. What I might actually start off on Friday is just rattle through a couple of problems. I have a worksheet of 5 or 6 of these that I'm gonna put up on Blackboard sometime before noon, as soon as I get back to my office at meeting. But I'll throw that up on there and you'll get to see, and we'll take a look at a couple of those and talk through and see if optimization problems are giving you trouble too. So anybody who's interested, we'll gather on Friday. Okay, have a good one, everyone.